So now what we're going to do is use a calculated heat of reaction by using the heats of formation. If you go to the tab Calc DHR, and at the top it says nitric oxide production using delta HR calculated from delta HF. You'll see it looks just like the previous spreadsheet, except if you go to cell F3, it shows an equation there in the heat of reaction. So recall that the reaction here is 4 ammonia plus 5 oxygens goes to 4 nitric oxides and 6 waters. And we called these, for shorthand, A, B, C, and D. And what we want to do here is create a hypothetical path involving the heats of formation. So we'll take all of our reactants and convert them to the elements as found in nature, which are N2, H2, and O2. This is all at 25 degrees C, and then we'll reconstitute those as the products. The heat of reaction for this step here can be expressed simply as the sum of these two legs of the journey here to the elements as found in nature and then back to the products. So we need to calculate this enthalpy here and this enthalpy, which I'll call delta H1 and 2. The heat in step 1 is actually the opposite of the heat of formation. Notice we're going from the molecules to the elements instead of the elements to the molecules. And so these will be the opposite of the heat of formation. So we'll have this is equal to minus 4 times the heat of formation of A, and then minus 5 times the heat of formation of B. The hat, remember, means specific enthalpy, kilojoules per mole, and the superscript 0 is standard conditions, 25 degrees C. The enthalpy involved in the second step, H2, is actually the heat of formation. We're going from the elements to the molecules. So we have 4 times delta H F of C and plus 6 delta H of formation of D. Now, what we need to do is add these two legs together, and that will be the heat of reaction. Change of the enthalpy of reaction is equal then, and I'm going to put the products first as I add these two things together. 4 times the heat of formation of C plus 6 times the heat of formation of D minus, because I'm adding these two steps together, minus 4 delta H F of A minus 5 delta H F formation of B. So you can think of this as the heats of formation of the products minus the heat of formation of the reactants. Each heat of formation multiplied by the stoichiometric coefficient. And of course the number, the actual heat of reaction, is the same. Sometimes it'll be off by just a tenth of a kilojoule per mole, perhaps, because it's just calculations, but it should be virtually identical. And in this case, to 4 places, it is identical. And so now the calculation of Q will be done exactly the same way. And so there's really no difference in those two spreadsheets, except for in the first one, given DHR, the heated reaction was just the given from the problem statement, and here we're confirming that really by calculating it using the heats of formation.